But which universe? Will the universe eventually stop expanding and start contracting, or will it expand forever? To answer this question, we need to know the present rate of expansion of the universe and its present average density. If the density is less than a certain critical value determined by the rate of expansion, the gravitational attraction will be too weak to halt the expansion. If the density is greater than the critical value, gravity will stop the expansion at some time in the future and cause the universe to recollapse. We can determine the present rate of expansion by measuring the velocities at which other galaxies are moving away from us using the Doppler effect. This can be done very accurately. However, the distances to the galaxies are not very well known because we can only measure them indirectly. So all we know is that the universe is expanding by between 5% and 10% every 1,000 million years. However, our uncertainty about the present average density of the universe is even greater. Add up the masses of all the stars that we can see in our galaxy and other galaxies. The total is less than 1/100th the amount required to halt the expansion of the universe, even in the lowest estimate of the rate of expansion. But we know that our galaxy and other galaxies must contain a large amount of dark matter which we cannot see directly.
And my brain
But which we
contains a
can
very large amount of dark humor.
there you go. Okay. But which we know must be there because of the influence of its gravitational attraction on the orbits of stars and gas in the galaxies.
Hey, wait. I have a question. If stars orbit around a black hole, what does the black hole orbit around?
Most likely the black hole is the center around which most other objects
The
rotate around it.
galaxy, but like,
Yeah.
what does the galaxy orbit around?
The galaxy is, if there's a black hole at the center, I think most black holes are at the centers of galaxies, right?
Yeah, but like, what does the galaxy, the whole thing, orbit around?
The whole thing is orbiting around itself, around its center. And sometimes there might be a black hole at the center,
I
sometimes.
know, but like, you just take the whole of the galaxy.
Hmm.
What is it doing like this?
Yeah, it is rotating around.
No. This is a galaxy. Is
Yeah.
it rotating around something here?
Oh, that way. No, I don't think it's rotating like that. No, the galaxy is what is rotating and it's just moving away from us. I don't think it's rotating around some other object.
Really?
Yeah. Okay, this is all my my you know my, what do they call it?
Idea.
Not even idea. It's my guess.
Contemplation.
It's my guess.
Contemplation.
No, it's my guess. I don't know much about this topic. I'm just reading a book right here. Okay. So,
You taught me.
where were we? Uh, yeah, but we know that our galaxy and other galaxies must contain a large amount of dark matter which we cannot see directly, but which we know must be there because of the influence of its gravitational attraction on the orbits of stars and gas in the galaxies. Moreover, most galaxies are found in clusters, and we can similarly infer the presence of yet more dark matter in between the galaxies in these clusters by its effect on the motion of the galaxies. So maybe galaxies and clusters do move around something else with you. I don't know. It's a good question to ask. We should try to find out. Yeah, we will try to find out.
Appa, do you know the expansion of the galaxy? Like, you have human, then you have city, state, country, then you have continent,
larger and larger
then you
thing.
have continent, supercontinent, planet, solar system, and then you go into galaxy, local group, Virgo supercluster, and it just keeps getting bigger and bigger. Then you have the massive universe, and then you have even more.
Other universes, multiverses.
Yeah, maybe the multiverse, maybe the multiverses.
Okay. Shall we continue?
But do you think there's any do you think there are more than one multiverses?
If there is more than one universe, I think there are infinite universes.
Is there more than one multiverse though?
I have no idea what that means.
No, like one multiverse there's all a common property to that multiverse. Like every universe has a common property in that multiverse.
You mean common laws?
No, just like one common, something in common.
Yeah, the laws that govern it.
One of the laws that.
Yeah, maybe in some other multiverse it's not relativity. It's a different form of relativity that governs us, or something like that, or maybe where conservation of energy doesn't hold true. I have no idea.
Or so, maybe where atoms can be produced.
Yeah, atoms can be produced even here.
No, like literally produced, just out of thin air.
Okay.
You can create new matter.
Yeah. Shall we continue reading? Because this is going so much into guessing and speculation that it's of no use, I think. But it's good. It's good to imagine. Maybe not when we're recording.
Yeah.
Okay. So.
Hey, why am I speaking in American accent? Actually, no, I am American.
Moreover, most galaxies are found in clusters, and we can similarly infer the presence of yet more dark matter in between the galaxies in these clusters by its effect on the motion of the galaxies. When we add up all this dark matter, we will still get only about 1/10 of the amount required to halt the expansion. However, there might be some other form of matter which we have not yet detected and which might still raise the average density of the universe up to the critical value needed to halt the expansion. The present evidence, therefore, suggests that the universe will probably expand forever. But don't bank on it. All we can really be sure of is that even if the universe is going to recollapse, it won't do so for at least another 10,000 million years, since it has already been expanding for at least that long. This should not unduly worry us, since by that time, unless we have colonies beyond the solar system, mankind will long since have died out, extinguished along with the death of our sun. The Big Bang. All of the Friedman solutions have the feature that at some time in the past, between 10 and 20,000 million years ago, the distance between neighboring galaxies must have been zero. At that time, which we call the Big Bang, the density of the universe and the curvature of space-time would have been infinite. This means that the general theory of relativity on which Friedman's solutions are based predicts that there is a singular point in the universe. All of our theories of science
are singular point as in what?
Singular point essentially means that literally things are, think about a function like 1 by x, okay? When x becomes 0, what happens to 1 by x? It becomes infinitely, yeah? That's a bad thing in science most often, because those kind of singularities are generally not good. Any solution like that?
You said there was a single point in the universe. What does
that
mean?
Singularity, na? Things are getting.
Well, I know the center of a black hole, but
no. Imagine if all the mass in the universe is getting compressed into a smaller and smaller and smaller point, and all of it goes into a single point. What will the density be at that point? Infinitely, yeah.
Well,
that is
related to the size of the universe, very, very large.
And it will be, but if it goes to a single point, that is still infinity, because the mass is finite, the volume has become 0, so it's infinite. That's not right.
Hey, but how is the volume 0? It's still a point, right? So
the point has no volume. No,
but there's got to be like some volume. It's
mathematical point technically has no volume.
Yes, but this is a scientific point.
No. Okay. These are the solutions to the mathematical equations.
This is an infinitely small point, but at the same time, it's not yet 0. It's like so infinitesimally above 0, but it's not yet 0. So it's got to have.
But it is tending towards that infinity, so the density goes towards infinity, so that's what is a problem.
Very close to infinity.
Very close to infinity. I'm sure that's a point that people can quibble over, but let's continue. All of our theories of science are formulated on the assumption that space-time is smooth and nearly flat, so that they would all break down at the Big Bang singularity, where the curvature of space-time is infinite. This means that even if there were events before the Big Bang, one could not use them to determine what would happen afterwards, because predictability would break down at the Big Bang. Correspondingly, if we know only what has happened since the Big Bang, we could not determine what happened beforehand. As far as we are concerned, events before the Big Bang can have no consequences, so they should not form part of the scientific model of the universe. We should therefore cut them out of the model and say that time had a beginning at the Big Bang. Most people do not like the idea that time has a beginning, probably because it smacks of divine intervention. The Catholic Church, on the other hand, had seized on the Big Bang model and in 1951 officially pronounced it to be in accordance with the Bible. There were a number of attempts to avoid the conclusion that there had been a Big Bang. The proposal that gained widest support was called the steady state theory. It was suggested in 1948 by two refugees from Nazi-occupied Austria, Hermann Bondi and Thomas Gold, together with the Briton Fred Hoyle, who had worked with them on the development of radar during the war. I think a famous Indian scientist was also there, Jayant Narlikar. I think he also had done a lot of work with the steady state theory, I think. Nevertheless, let's continue. The idea was that as the galaxies moved away from each other, new galaxies were continually forming in the gaps between them from new matter that was being continually created. The universe would therefore look roughly the same at all times as well as all points of space. The steady-state theory required a modification of general relativity to allow for the continual creation of matter, but the rate that was involved was so low, about 1 particle per cubic kilometer per year, that it was not in conflict with experiment. The theory was a good scientific theory in the sense that it was simple and it made definite predictions that could be tested by observation. One of these predictions was that the number of galaxies or similar objects in any given volume of space should be the same wherever and whenever we look in the universe. In the late 1950s and early 1960s, a survey of sources of radio waves from outer space was carried out at Cambridge by a group of astronomers led by Martin Ryle. The Cambridge group showed that most of these radio sources must lie outside our galaxy, and also that there were many more weak sources than strong ones. They interpreted the weak sources as being the more distant ones and the strong ones as being near. Then there appeared to be fewer sources per unit volume of space for the nearby sources than for the distant ones. This could have meant that we were at the center of a great region in the universe in which the sources were fewer than elsewhere. Alternatively, it could have meant that the sources were more numerous in the past at the time that the radio waves left on their journey to us than they are now. Either explanation contradicted the predictions of the steady state theory. Moreover, the discovery of microwave radiation by Penzias and Wilson in 1965 also indicated that the universe must have been much denser in the past. The steady state theory therefore had regretfully to be abandoned. Another attempt to avoid the conclusion that there must have been a Big Bang and therefore a beginning of time was made by two Russian scientists, Yevgeny Lifshitz and Isaac Kalatnikov in 1963. They suggested that the
It's
Big Bang...
but yeah.
Fine. They suggested that the Big Bang might be a peculiarity of Friedman's models alone, which after all were only approximations to the real universe. Perhaps of all the models that were roughly like the real universe, only Friedman's would contain a Big Bang singularity. In Friedman's models, the galaxies are all moving directly away from each other, so it is not surprising that at some point in the past they were all at the same place. In the real universe, however, the galaxies are not just moving directly away from each other, they must have small sideways velocities. So in reality, they need never have been all exactly at the same place, only very close together. Perhaps then, the current expanding universe resulted not from a Big Bang singularity, but from an earlier contracting phase. As the universe had collapsed, the particles in it might not have all collided, but they might have flown past and then away from each other, producing the present expansion of the universe. How then could we tell whether the real universe should have started out with a Big Bang?